the class, you all can hear me, right? What is the thickness?
Is it still 0.2 inches?
Well done. Okay. The thickness is still 0.2. Okay, the thickness is still 0.2 because if you look at A down here, right, I'm gonna say is this section that we're going to consider. All right, relative to the end, it pulls itself back. Okay, still analyzed from Y max, right? The analysis will still go from Y max. Right? Again, the rules that so the analysis, so this is still our datum, right? Analysis will start from what? Remember we said the analysis will start from Y max, right? And this is the analysis direction. I was telling a student today, these 4 rules, okay, that I bestowed upon you guys, it took me 3 years to develop, to really understand. Okay, that's why I want you guys to be better than me. Okay, I want you guys to see this earlier, and shearing stretch is not a difficult topic at all. Okay, so now we have this. So again, V and I are constant. So that's an easy one. Okay, so now when we take from here, okay, so when we do this now, so we're going to find a Q at point A now. Okay, so I like to again width depth multiplied by Y bar, right? So the width over here is equal to so that is 0.7. The width is 0.7. Depth is 0.2. Y bar is 1.5 minus by 0.2 divided by 2. Okay, so this will become 0.7 times 0.2 times by 1.5 minus 0.1 is equal to 0.196 inches cubed. Right? So from here, we're going to find the shear stress at point A. So this is equal to VQ. V theta, come on. VQ divided by IT. Right? So V, don't know what is it. I did not bother to calculate. Q is 0.196. Right? The thickness is equal to 0.2. Right? And I'll write this out. You don't need to write this, but I'll write this out. The down here, I'll multiply by 1. In fact, you don't need to write this one. This is because Q is equal to what? 1Q. Yes or no? It's just Q. It's not equal to what? 2Q. Yes or no? Right? That's why it's 1. Okay? So this will be equal to 0.196 divided by 2 divided by 1. So it's equal to V over I 0.98. Okay? So what we realize from here is, hey, not something is weird, but for this question, right? The at point B, right? The shear stress is also 0.98 divided by B over I. Yes or no? Right? And then at the point A, it's still the same. So now we are going to consider the centroid. Okay? And listen, I'm going to do the centroid 2 ways. One way is we're going to do from the top. Okay, one way we're going to do from the top. The other way is we're going to do from the where? From the bottom, right? If our concept works, it does not matter whether you work from the top or from the bottom. I repeat again, if our concept works, it does not matter if you want to find a centroid, it does not matter whether you get it from the top or from the bottom. The answer has to be the what? The same. If the answer is wrong, there's something wrong with our analysis. Okay. Now, guys, I know that I've passed your break time. You all want to go for a break or no? Anyone? Or you want me to push on? I'm so high now that I don't want to stop. How about you guys?
Keep going, sir. Keep going.
Okay. So I will push ahead. Okay. Now, I want you to watch this now. Okay. I want you to watch this now. Hold on. I'm so excited now. Oh God. My wife sometimes says that I need drugs to calm down. Okay, I do. I need some cookie, man. Oh shoot, this is recorded. Oh crap. Anyway, right. So now we're going to find. Yeah, I'll try to do this on one page, so you can compare and contrast. Okay, what a term. Okay, so we are going to look it from. So I'm going to find. Okay. Okay, I'm going to call this. So this is our centroid. Right, this is our centroid, and then we're going to find point C. Okay, point C, and we're going to analyze based on thin wall box beam. Okay, I need to find out, make sure there's enough space. Okay, thin wall box beam. Okay, so I'm going to cover it. Okay, so this is point C that we're going to find, and we will see that you can see that the Q is going both ways, right? So this is the Q. So because it's box beam, we're going to declare this as what? 2Q, right? So again, the shear stress at point C is equal to VQ over IT, like what before. V and I are constant. T now is equal to 0.3 inches, right? It's perpendicular to the what? To the shear flow, right? So we're going to find Q at point C. So Q at point C, I'm going to section the structure in this way, okay? Let me change color. So I'm going to call this my flange, okay? So again, this will be equal. So in fact, we have this value, right? So the width is equal to 2 minus by 0.3, 0.3. Hey, Eugene, come on, calm down. Thickness is 0.2. Centroid is 1.5 minus by 0.2 divided by 2, right? And then plus, so the width is 0.3. The depth is 1.5 multiply. So there's a 2 because there's a left and right. You have a 2 in the front. Okay, the 2 because you have what? You have a left and you have a right. Okay, so you have a 2 down here plus by 2 multiply by the width multiply by the depth multiply by y bar divided by 2. Right, so this over here is for left and right. Okay, so this will be equal. So the first one is 2 minus 0.3 minus 0.3 times by 0.2 times by 1.5 minus by 0.1 close bracket. So it's 0.392, like what we had before, plus 2 times 0.3 times 1.5 times 1.5 divided by 2 is equal to 0.675. So this will be equal to 0.392 plus 1.675 is equal to 1.067. Okay, this is what we got. So from here, the shear stress at point C is equal to VQ divided, Q, sorry, Eugene, 1.067 divided by I, and the T is equal to 0.3 box beam you times 2. Okay, so 1.067 divided by 0.3 divided by 2. The answer is, wait, what did I get? 0.672. Is equal to 1.778. Okay, 1.778 V over I. Okay, so this value seems to be a bigger bigger value. Yes or no? Okay. Okay. Now, next, what I'm going to do is I'm going to do the same analysis, but I'm going to look at the bottom part. Okay, I'm going to look at the bottom part. Okay, so this is what we got. Okay, so this is the first moment of area. Okay, now I'm going to do the bottom part. Okay, hopefully I think I have enough space. Wait, oh, it's going to be tight, but it's okay. Let me see, can I move this for you guys? Yeah, I can. Okay, again, I'm going to cover the top part. Okay, this is our centroid. Okay, at this point is our point C. Okay, I'm just going to move over. I'm going to copy this. I'm going to paste this. Okay, so I'm going to draw the shear. I'm going to draw the shear flow now. Okay. Okay, so that is our shear flow. So now, as we already know, this is a wide flange, right? Wide flange analysis, wide flange thin wall analysis. Right. So the only area that we need to consider is this area. The one I shaded. The one on the left hand side, you can ignore it. Why? They have the different start. Come on. They hold on. Something happened. Too excited again. They have a different start point, and they have different what? End point. Yes or no? Okay. Do apologize. Let me adjust the screen so you can see. Right? They have different start point, and they have different what? End point, as you can see. Right? So again, I'll repeat what I've just said, that this over here, you have the start point here, number 1. You have end point number 1. You have start point number 2. You have end point number what? Number 2. So that is why you can ignore the shear flow on the left hand side. Then you will say, Eugene, where do you teach this? Okay, we did. Okay, so when I introduce you into here, right? What did I tell you? If we were to find alpha, right? We don't care what is happening on the right hand side, right? We just care what is happening on the alpha side relative from the start point, right? So that's where I told you, right? We're going to apply the theory on what we learn on this analysis. There you go. Okay. So now once we get it, you understand, yes or no, right? Because what happened on the left hand side have nothing to do on the what right hand side at all. Okay, for a wide flange. For a box beam, it starts from the center, it goes left and right. You have to consider it. Okay, so again, more rules to apply. That's why this topic is so abstract. Okay, it's just rules and rules and rules. Okay, so from here we do a wide flange thin wall analysis. Okay, so now we know that we only need to consider what? 1Q, right? We don't need to consider on the other side, they have different start point. Okay, you don't need to bother. Okay, so now the thing is, our first moment of area has to be the same. If it's not the same, okay, we might be in a bit of trouble. or I don't know. No, it can be different. Okay, but the shear stress, okay, the shear stress at point C, whether you take from the top or the bottom, okay, has to be the same. Okay, let's go. So Q at point C. Okay, so the width is 0.7. The depth is 0.2. 1.5 minus 0.2 divided by 2 plus The width is what is the width? I think it's 0.3. 0.3